The sum of an infinite or infinite geometric series or infinite geometric progression. We got a little case here where a guy is travelling and he's halving his step size or jump size. Will he ever reach point B if he starts at point A? So if we have a certain unit, then we halve it each time. The theory goes he'll never get there, and that's a little paradox that's being used. There's many different versions of that out there. So if you think that through yourself, you might agree in theory with that paradox. However, practically, perhaps it doesn't work. And a certain Greek philosopher had a version of it where the runner was doing his journey from A to B in different stages, and you can see that would be an example like that. And if he ran the first stage in this ratio and then it was half for the next, so half the distance in the first stage, and then he did a quarter, then he did an eighth and a 16th and so on. He argued because it would take an infinite number of stages to get there, he would never get there. So you could probably think of some practical limitations where that might not stack up, but in theory this philosopher is correct. Have a think about it, pause the video if you want to think about that to its fullest extent. So you can also examine the idea by looking at different geometric series. This geometric sequence here, we can find the series by adding all of the terms together. This one's infinite, keeps going. If we added the first 9 terms together, you can get your calculator out and verify it, you'll get that answer there. If you add the first 20 terms, you'll get that answer there. And it appears that if n was approaching infinity, the closer and closer it gets to infinity, we can see that it's approaching 0.5. So there's our little symbol for approaching. So S of n, for n terms, as n gets bigger and bigger approaching infinity, S of n or S sub n approaches 0.5 for that particular sequence there if we sum the terms to find the series. We can say for ones like this it approaches something, or it converges on something, or it's a convergent series. Okay, so this one is convergent, and we can say that a series, an infinite series, is convergent for the terms if the sum of the first n terms, which is S sub n, approaches what we call a limiting value if we see the trend as n approaches infinity, where we can look at increasingly longer sums and increasingly more terms. So the ultimate extent of that would be infinity. The limit, or the limiting value, that's an important word, limit, it's called the sum to infinity of the series. And we're dealing with cases here where r is a fractional value or a decimal value between 0 and 1, or it is between -1 and 0. So in other words, putting all that together, from -1 up to 1 exclusive. Okay, so your common ratio cannot be 1 or over, and it cannot be -1 or under. So we have those sort of situations like we just saw above in both of those examples. You can see that the common ratio is fractional. Okay, it's 1/3 there, for example, and the common ratio from one term to the next is a half. Okay, and it works for negatives as well. Okay, so if r is between -1 and 1 exclusive, the infinite geometric series, the sum of the sequence, is convergent, and the sum to infinity is given by this formula here. So that's important to note. And remember, we have our same values that we have been dealing with. So that's the first value, or the starting value. That's the same as everything we've done before, and r is a common ratio. Alright, that's no different to the previous study we've done. to show that it works, we can look at S sub n, the sum of the series that we've seen in the past, which expanded out is like that. Okay, so they expanded the numerator and then separated the two elements of the numerator with their same denominator, and as n, the number of terms, approaches infinity for bigger and bigger values, we look at the effect of r to the n, and if we have that, we have r to the infinity, because remember, this is a case of where r is a number between -1 and 0 and 1 and 0 and 1, and if you've got, say, an example of that, say 0.2, and if you've got, say, 0.2 there just as one example, if you keep raising it to higher powers, it gets smaller and smaller and smaller, and if it's negative, it'll get the same way. Alright, if we've got -0.1, if we keep squaring, -0.1 squared is positive 0.01, and then times that by -0.1 again, and we get -0.001. So it alternates between positive and negative, but look, it's getting smaller and smaller. It's still approaching 0, but from the other side. So they do approach 0. That would mean that if that approaches 0, that whole numerator there approaches 0, which means that whole fraction there approaches 0. And so it approaches, that'll all get knocked out, and basically that there will approach, it doesn't have an n on it, alright, so it's unaffected by the value of n. It'll approach a over 1 minus r, and hence this is where we get the formula from up here. So see how it's a over 1 minus r. Here's an example that uses it, and express the recurring decimal 0.32 recurring. Now that's the 3 and the 2 have dots on them. I'll make those dots bigger. So 0.32 recurring is 0.323232 ad infinitum. So how does that relate to what we've just learnt above? Alright, so I'll just pop the formula down. Sum to infinity. First we need to identify, if it is going to work with that, we need to identify an A and then an R. Well, we've got some work to do because we can't see that there just with that number, but if we look at how that number there is made up, it's 0.32 plus 0.0032 plus 0.000032 ad infinitum. Now we do, if you look closely, we do have terms. We've got A, AR, AR squared, and so on. So A equals 0.32. What's R? So we're multiplying. See how we're getting another 2 empty place holding situations with 0, 0. Each succeeding term is 1/100th of the previous one, okay, because the decimal has gone 1, 2 to the left there, and another 2 to the left there, and so that's 100th. And so we've got our elements we need, and so the sum of the series will equal, to infinity, it will equal 0.32 over 1 minus 0.01, which is 0.32 over 0.99. Now we have to write it as a ratio of two integers, in other words a rational number, so we have an integer over an integer. That's called a rational number, you might have heard that. So some integer a over some integer b. Well, if we look at our answer, we haven't got integers, but we could write that as an equivalent fraction, 32 over 99.